Okay. Okay, now it's time to start. So, all right. So if you remember back on the very first day, I gave you an outline of the entire course, and I said we would do 2 days on spherical Coxeter groups, finite Coxeter groups, 2 days on Euclidean Coxeter groups, and then 2 days on general Coxeter groups. But it turns out, now that we've actually had 4 days of lecture, that I still have things I want to say about these. And so, and we're just getting to some interesting things. And so I actually want to spend the first half of the day still on the Euclidean Coxeter groups. And then hopefully by the end of the hour, we'll have a definition of a general Coxeter group. Okay? Because the first thing I want to do is I want to actually give you some of the answers for the exercise that I gave you last time. And when you start doing this, so what was the exercise? The exercise was to, you remember what these were, right? That this was, out of the n coordinates, you select 2 coordinates to be non-zero, and you can choose signs however you want. Okay, and that gives you the dn root system. And then the exercise was to find roots that look, for example, let's just do a particular one, like this, with this kind of arrangement. And one thing that you probably found right away is that you found yourself writing things like E1 minus E2, and you might want a shorthand notation, right? And so let me give you a shorthand notation. So this is a shorthand notation. For common roots, and I should say this is a non-standard shorthand notation for common roots, but it's something that another mathematician, John Crisp, and I came up with for our own work, and I found it very useful, and so actually I'll be using it in a paper that I'm publishing soon. And the shorthand goes like this, that, let me just do it by example, that if I'm doing E1 plus E2, I'm going to write this as 1, 2 slash. Okay? The 1 and the 2 refer to which vectors we have. And I'll tell you what the slash means in just a second, but hopefully you can actually figure it out. E1 minus E2 is this. Minus E1 minus E2 is that. Okay? And then minus E1 plus E2, 2/1. Okay? Numbers before the slash, are positive. Numbers after the slash are negative. Okay? And so then you could easily see something like, what if I wrote that? Then that's something in here. Right? And it's a little bit easier to write. All right. And in fact, you can see that it's in here because how many minuses? There's 4 minuses. Right? So it's very easy to spot what happens, and once you get used to the notation, it's very easy to see what dot products are. And so one answer for the D in root system is you could do something like this. You could do 1, 2 slash, let's see, yeah, 2/1. Here I could do 3/2, 4/3, 5/4, /5, 6, 6/5. Right, and you're going to see the number they have in common is the 2's. One's positive, one's negative, the dot product's negative. The number they have in common is 2, one's positive, one's negative, and you can just see that those all work. When you get far apart, these two, you have a +1 and a -1, and so they really are 0, and far apart they don't have the same numbers at all. And so they really are 0. Okay? So like I said, this is non-standard. You won't find this in any text, but at least from my own, when I'm working at a blackboard, I find this very useful because it's a nice compact notation and lets me check things. Okay? The second half of the exercise was to find the linear dependency. Right? And with this one, what's the linear dependency? Well, let's see. Whatever number of these you have, so you probably got different answers, right? But if you think about it, the diagram is encoding the dihedral angles. The diagram is encoding a vector arrangement. My arrangement of vectors is describing a set of hyperplanes that are bounding a particular fundamental domain. Your set of vectors are the same, they're just in a different position, right? There's a nice isometry from my vectors to your vectors. They're bounding hyperplanes, bounding a fundamental domain, so you just selected a different fundamental domain than I did. Okay? But there are many different correct answers, one for every fundamental domain. Okay? All right. In any case, because my arrangement of vectors and your arrangement of vectors are isometric, my linear dependency and your linear dependency will have the same coefficients. Right? And so the coefficients of the linear dependency are independent of which fundamental domain. I should say that this collection of vectors, so this is called a root system. This collection of, well, let me just say it in general, n+1 vectors is called a simple system. Okay? One for every dot. When you have one for every dot, that's called a simple system. The hyperplanes that bound your fundamental domain, that's called a simple system. Okay? All right. So, what's the linear dependency here? Let's try and do it as simply as we can. So let's just say that we have one of these. Okay? And now we just start working through. If we have one of those, the only place the first coordinate occurs is right here and here. And so if I have one of those, I need one of these. Right? But now if I add these two, I have 2 in the second coordinate. This is the only other place that 2 occurs, the second coordinate occurs. And so I better have 2 of those as well, right? But then I have a plus 2 in the third coordinate, and this is a -1, so I need 2 of those. And 2 of those, you sort of work your way across, and then 1 and 1. And so the pattern for the D, the answer that you should have found is something that looks like this. Right? Okay. With some of the ones like the B and the C and the F, they can be slightly complicated. The only other one that I want to do as an illustration of how this works is the most complicated exceptional case, which is the E6. And so let me go ahead and show you what happens with the, E8. With E8, One, 2, 3, 4, 5, 6, 7, 8. This is the extra dot. All right. And by introducing this notation, then it's going to be straightforward for me to write these down. And the answer that I want is 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. That's sort of a nice way to get going straight across. And then for this final one, for this final one, now I'm going to have to start using some of these others. These final ones, actually, let me not do 7/8. Sorry, I want to do 7, 8 slash. Because what that allows me to do, this just makes it a little bit nicer. I can do slash 1, 2, 3, 4, 5, 6, 7, 8. All negative. Because the fact that the first and second coordinates are both negative means that it's perpendicular to that. This says the first 2 coordinates have to have the same sign. This says the second and third coordinate have the same sign. Third and fourth have the same sign. Fourth and fifth have the same sign. Fifth and sixth have the same sign. Sixth and seventh have the same sign. Seventh and eighth don't need to have the same sign because we want this to have a -1 dot product. Yeah? So far so good. And then I want something up here. And so let's see if you can figure out what should happen here. Because I want it perpendicular to this and perpendicular to that, the first 3 coordinates should all have the same sign. Right? Because if I want something dotted with this to be 0, this is positive, that's negative. 1 and 2 better have the same sign. Right? So 1, 2, and 3 have the same sign. And then this one says 4 and 5 have the same sign, 5 and 6 have the same sign, 6 and 7 have the same sign. So 4, 5, 6, 7 all have the same sign. 7 and 8 need to have opposite signs. Being perpendicular to this means that I need to have 4 positives and 4 negatives. And so what you should end up coming up with is that this is really the only thing that works, and it does work. Because 1, 2, and 3 have the same sign, 4, 5, 6, 7 have the same sign, 7 and 8 have opposite signs, and there are 4 positives and 4 negatives. Okay? So this is a simple system for the E8 root system. And sorry, what? Oh, the dot product with 3, 4. Oh, that's positive 1. Ah, you're right. But that's easy to fix, right? Yeah, since this dot product was positive 1, I just need to switch the 2 sides. Okay. Great, thanks. There we go. There we go. Okay. And then for the let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then the linear dependency is sort of interesting. I won't go through and argue it for you, but the answer is this. The answer is 6 of those, 4 of those, 2 of those, 3 of those, 5 of those, 4 of those, 3 of those, 2 of those, and 1 of those. And so they're actually nice linear progressions on all the 3 arms. And so this is the unique linear dependency among the vectors. Okay. All right. the few other things that I want to tell you, so there's a few other things that I want to tell you. First off, I haven't told you root systems for all of the Euclidean Artin groups yet. I've told you root systems from last time. What did we have? We had root systems for dn, for bn, for cn, tilde, for f4, and for f8, or e8. I didn't tell you ones for G2, but we drew it. This one we had a picture, right? And so there's actually not a nice, I mean, you could write coordinates, but it's easier just to draw the picture for G2. But the ones that I haven't done is and we drew a picture for A1, tilde, right? That was just the interval on the line. So the ones that we haven't done AN, and we haven't done E6 and E7, so I want to say a word about those. And the other thing that I want to do, actually, before I leave linear dependencies, let me just prove a quick lemma for you. Just because I think this is a nice lemma to know. If V is a collection of vectors that are pairwise non-acute, so dot products are always 0 or negative, then any, I'm going to throw in the word minimal linear dependency has only positive coefficients. And so this lemma is just supposed to take the mystery out of the why the linear dependencies use positive numbers. Okay? Simple systems have this property of being pairwise non-acute. All the angles are pi over 2 or bigger. And so if there's a linear dependency, it has to involve positive coefficients. And the proof is just by contradiction. And it's a nice slick little proof. So suppose not. Then what does that mean? That means that we can find, so there exist coefficients, I don't know what you want to call them, Ci not equal to 0. So some subset of these have a linear dependency, right? Let me just go ahead and write something like C1, V1. So this will be easier if I just say it in words. So because we're assuming that there's a linear dependency that doesn't just have positive coefficients, or if they all have negative, there is a linear dependency that has both positive and negative, right? And if there's a linear dependency with positive and negative coefficients, then what I want to do is this is set equal to 0, I want to take the ones with negative coefficients and I'm going to move them to the other side. Okay? And because it's minimal, so what I now have is that a positive linear combination of a set of vectors is a positive linear combination of a different set of vectors, right? And they're equal. Okay, so that's what I want to write. So what I want to write is that, C1 V1 plus CK VK is equal to some D1 U1 plus DL UL. Right? I don't want to worry too much about notation, but I have some set of vectors with positive coefficients added up together, some set of vectors with positive coefficients added up together. Yep? Okay. The vectors involved are distinct. I'm also assuming minimal. And because I'm assuming minimal, that means that this vector that I get is not 0. Right? Because otherwise here's a linear dependency that's smaller. Okay? So minimal means that this is not 0. So let's give it a name. Let's call this W. What can you tell me about the number W dot W? If I take W, if I take a vector W, and I take W dot W, and W is not 0, what do you know? You don't know a lot, but you know something, right? What do you know? W dot W, positive, right? Any vector dot with itself is positive. But now I want to represent W as this for the first W, and I want to represent it as this for the second W. And when I take this dot this, I'm getting W dot W. But now when you expand it, what do you have? You have positive coefficients, non-positive dot products, because they're pairwise non-acute. And so the total answer, when you consider W dot W and you view it as C1 V1 plus dot 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 dotted with D1 U1 plus dot dot dot, then what you get is you get Ci dj Vi dot Uj, and those terms are all non-positive. Each term is non-positive, and so this is less than or equal to 0 contradiction, because this is positive. Right? When you think of it as W dot W, it's positive, but when you think of it as this dot this and expand, it's less than or equal to 0. Contradiction, this can't happen. And so that's why the linear dependencies have positive terms. Okay? One thing that's nice about having a linear dependency with positive terms is that it actually means that your vectors, when you have a linear dependency with positive terms, what that ends up meaning is that the space spanned by these vectors is some subspace. Every point in that subspace can be written as a positive linear combination of the vectors. Right? Because what you do is you say, well, if it's in the span, it's a linear combination of these vectors. But now take this linear dependency that we have with all positive coefficients. That's 0. Just add it to your linear to the description of your point, and you can make all the coefficients positive. And so every point can be described as a positive linear combination of the vectors in your subspace. What's slightly surprising is the fact that these yellow numbers are integers. And that has to do with the fact that we're looking at very, very special arrangements of vectors. Okay. All right. Next, I want to give you the rest of the root systems. So more root systems. So the root system for AN, is actually very easy. It's the root system for Dn plus 1. So this one, just one dimension up. Dn plus 1, but you look at the things that are perpendicular to the vector with all ones. So what does that mean? So what is this system? So the Dn root system is just you have two numbers. You have ei plus or minus ei plus or minus ej. When I make sure that it's perpendicular to this, now which ones am I looking at? Ei minus ej, right? One's positive, one's negative. So it's all the things of the form I slash j, right? It's all the things of the form I slash j. I can be bigger than j, j can be bigger than I. We have all of them. One quick comment about that is that if you look at the vectors, so suppose we are in the plane spanned by ei and ej. Where is ei minus ej? What vector does it look like? Ei minus ej, there's ei, there's minus ej, so it's this vector. What's the hyperplane look like? Hyperplane looks like this. And so what happens when you reflect in that hyperplane? You go from this. And so what does this do? This root corresponds to a reflection switches the ith and jth coordinates. Right? It just switches the ith and jth coordinates. If you have a point xi, yj, then where is it going to go? It's going to go over to yj, xi. It just switches them. Right? I guess I can make them both x's. Okay. In particular, when you look at all of these roots, what happens to Rn? If I take a point in Rn, if I take a point, or Rn plus 1, if I take a point in Rn plus 1 and I start applying all of these reflections, what do they cumulatively do? What can I do? Using this particular reflection, I can switch the I and jth coordinates. Using all of these reflections, I can permute at will. I can permute them all around however I want. And so the group that I'm getting really is the symmetric group on n plus 1 things. Right? And so this is the natural root system for an. It's easiest to see it, like we saw before, it's easiest to see it one dimension up, like we did when we drew the triangle in R3 rather than in R2. And that's the place where it's easiest to see the root system as well, is to look at it one dimension up. Okay, so that's the A root system. The only other ones that we haven't done are the E6 and E7, and for those, I'm just going to make a quick statement. And that is, the easiest way to construct the E7 root system is to consider all roots in the E8 root system perpendicular to any fixed root. Okay, so you take the E8 root system, you select one root, and you look perpendicular to it. You're in 8-dimensional space, you pick one root, you look perpendicular, there's going to be a 7-dimensional space. Some of the roots will be in there, some of them will not. This one has 240 things. When you look perpendicular, 126 of them will be perpendicular, and they will form an E7 root system. Okay? And in fact, it doesn't matter which one you pick, because all the roots look the same. It's a this set of 240 roots is very, very, very symmetric. Okay? And in fact, let me give you a sense of how symmetric. So we're in 8-dimensional space. We have 8 coordinates. We have 240 vectors. Right? And now I say consider the symmetries of this arrangement. 240 vectors. Right? When we reflect with this vector, these 240 things are going to be sent to themselves. Right? Because they're describing some arrangement, and that arrangement is preserved. They have the number of symmetries of this arrangement of vectors. There are roughly 700 million symmetries. Okay? 700 million. In fact, I have the exact number, so let me write it down. So the size of the isometry group of the E8 Coxeter group, which is the same as the size of the isometry group of the E8 root system, is 696,729,600. Okay? This is what I mean when I say very, very symmetric. Okay? This is a very, very nice arrangement of vectors. This is a very, very nice arrangement of vectors. Okay. In fact, if you take these 240 vectors and you select out this one, and if you select out a vector and I select out a vector, there's a symmetry that moves my vector to your vector. If I select out two perpendicular vectors, and you select two perpendicular vectors, there's a symmetry that moves my pair to your pair. First one to first one, second one to second one. If I select three perpendicular vectors, and you select three perpendicular vectors, there's a symmetry that moves my triple to your triple, with the first one going to first one, second, third to third. Okay? Similarly, if I pick out two vectors with a 60-degree angle, and you pick out two vectors with a 60-degree angle, there's a symmetry. If I pick out two vectors with a 120-degree angle, and you pick out two vectors with 100, there's a symmetry. Okay? And so I'm not going to write it down, but it's almost the same sentence. The easiest way to construct the E6 root system is to select two non-perpendicular vectors, look at the two-dimensional plane that they span, and look at the 6 dimensions perpendicular. Okay? Two non-perpendicular vectors describe a plane. There's 6 dimensions perpendicular, and that 6-dimensional space, there'll end up being 72 of these vectors in it, and those 72 vectors form an E6 root system. And so the upshot for this is that the AN root system actually sits inside the DN plus 1 root system. The E6 root system sits inside the E7 root system, sits inside the E8 root system. And so once you get a good feel for the E8 root system, you actually have an understanding of this group and this group. And because the roots are contained inside, the groups are contained inside. Because that means the reflections that generate the group are contained in the reflections that generate this group. Okay? All right. So I want to say one last thing before we move away from the Euclidean. Yeah, let's go ahead. Okay. Oh, actually, since I just erased it, what about the reflection that corresponds to a vector like this? What is this? This is just EI, right? When I reflect perpendicular to EI, what does that do? It just changes sign, right? These kind of reflections, this changes sign. In the ith coordinate. Okay, and the last one, just to, because in the part that I erased, the most common roots to see are the ones of the form where you select one coordinate or you select two coordinates. When you've got something with only one coordinate, positive or negative, what you're doing is you're doing a sign change in that one coordinate. When you select two coordinates, we saw that when you look at a reflection like this, where the two coordinates have different signs, that you're switching the coordinates. The last one that I want to consider is, what about that? What happens if I look in the EI-EJ plane and I consider the vector EI plus EJ? If I look at EI plus EJ, then what is that doing? The hyperplane looks like this, and it would send a point of the form xy, and where would it send it? It would send it somewhere. Let's try that again. It's going to send this part to that part. It's going to send this part over to that part, right? And so what is that? Instead of having plus x plus y, it will end up being minus y minus x, right? And so what is this kind of root doing? This kind of root, it's switching coordinate, changing both signs. Right? Switching the coordinates, changing both signs. which sounds slightly complicated, but now what happens if I multiplied Eij times Ei slash j? What's the product of those two? This one is going to reflect, and the other one is going to reflect like this. I'm going to do a reflection like this and a reflection like that. It's going to be a pi rotation. And so the product of the two is going to be a pi rotation. What does that look like in terms of the coordinates? Change two signs. Right? And so when you have freedom to have whatever signs you want, then you can do two sign changes as a product of two reflections. And so when you think about the D root system only has things like this. You're not allowed to change one sign, but because you have things of this form, you're allowed to permute coordinates. Because you have things of this form, you're allowed to permute coordinates and change an even number of signs. And that's actually what the D root system allows you to do. Arbitrary permutation, even number of sign changes. Okay? Arbitrary permutation, even number of sign changes. The type B group, where it has this kind of situation as well, arbitrary permutation, arbitrary sign changes. And so those are actually, the finite group A, B, and D are just arbitrary permutation, arbitrary sign changes, arbitrary permutation, even number of sign changes. Okay. All right. I want to do one last thing. Okay. So, all right. So, one last comment about Euclidean Coxeter groups. So, these 11 types of diagrams, or 10 types of diagrams that we have listed there, and in the corresponding finite ones. The things, there's one thing that I want to say about this, just to try and encourage you to investigate these further, and that is that, let me say this in a general way. Every spherical Coxeter group and Euclidean Coxeter group has numbers associated to it. Okay? So let's just call this numerology. Okay? All kinds of number patterns. There's number patterns for these things. So let me give you a couple of numbers. So first off, little n, you've been seeing a lot. This is just the dimension. Right? And so like E8, 8 is the dimension. We're talking about an 8-dimensional reflection group. Okay? Capital N is the number of reflections. And let me just say, twice capital N equals the number of roots. And so like in the E8 case, we said there were 240 vectors. There's 240 vectors, but they come in pairs. This vector and this vector define the same hyperplane. And so the number of roots is always an even number, and cutting it in half, that gives us the number of reflections. Yeah? Okay. Now is where it gets a little bit interesting. There's another number called H, which is called the Coxeter number. And there are many definitions of the Coxeter number, but the one that I'm going to use here, because it's easiest to write down, is that H NH equals 2n. Okay? It turns out that the number of reflections is that twice the number of reflections is always divisible by the dimension. It's not obvious why that should be true, but it's true, and this turns out to be an integer. Okay? And let's do the E8 example as we go through here. So n is 8, capital N is 120, twice n is 240, which is the size of the E8 root system. And so now what is little h in this case? 30. Yeah, little h is 30. Okay? All right. Now there's a set of n numbers. So these are not the same EI as before. The EI are actually integers. Okay, different EI. I have to call them this because these are called the exponents. So W is the Coxeter group. And it's W because it's named after Hermann Weyl. Hermann Weyl was a mathematician that studied these a lot, and he gets Coxeter groups named after him, at least the first initial. So Coxeter groups are often labeled W. There's exponents, which are a sequence of integers, okay? And then there's a second sequence of integers called the degrees. Of W. And now I just want to tell you a couple of facts, and we'll do the E8 case. Let me leave the E8 case. Let me actually do it for... Let me give you part of the list. It starts at 1, and it goes up to 29, and there's 8 numbers. Okay? The degrees... So here are two nice facts. If k is a positive integer less than n, and the GCD of k and h is 1, then k is an exponent. Okay? It's just a nice fact. Okay? And so let's apply that in the E8 case. So 1 and 30, those are relatively prime. Right? So let's see. So what other numbers are relatively prime to 30? You might start with some primes, right? Primes are a good source. So you want to avoid the primes that are in there. So you don't look at 2, you don't look at 3, you don't look at 5. 7? Sure, 7 works. And actually, 23 works. Because if 7 works, then 30 minus 7 should work, right, for GCD. What else? 11 and 19. Didn't leave myself enough space. 13, 17, and that's it. We got all 8. This doesn't always work, but for this particular group, this one fact tells you all 8 exponents. Okay? This one fact tells you all 8 exponents. The second nice fact, DI equals EI plus 1. The second list is just a modification of the first list. You just take these and you add 1 to everything. Okay? So there's redundant information here. So what's the list of degrees? 2, 8, 12, 14, 18, 20, 24, and 30. Right? Okay. So, actually, let's make this 4 nice facts. Because now I want to tell you why these are interesting numbers to have around. One reason for liking the exponents is that the sum of the exponents, I don't know if you can add those 8 numbers very quickly, but using the matching, it's not that bad, because that's 30, 30, 30, 30. Right? So it's 120, or in general, it's equal to n. Degrees are nice because the product of the degrees is the size of the group. And if you multiply these together, you'll get the 696,729,600 that we had before. Okay? And this is not just something that happens with E8, it happens with all of them. They all have a little n, a capital N, and H, a list of integers, And they have very nice properties. Okay? And in fact, if you go deeper into the study of Coxeter groups, there are many different parts of mathematics where the spherical Coxeter groups and the Euclidean Coxeter groups show up. And often when you have an application of Coxeter theory in a particular part of mathematics, like in algebraic geometry or in the theory of polynomial invariance, then these are actually called degrees, because if you look at certain polynomial algebras, there's a certain polynomial algebra, a set of polynomial invariants that have a free basis, and these are the degrees of the polynomials that show up in the basis of the polynomial of the algebra of polynomial invariance. Okay, and so it's good to, so all I'm doing here is I want you to know that there are at least these 5 sets of numbers for any finite Coxeter group, and the 5 sets of numbers have lots of relations between them, and they're useful for other parts of mathematics. Okay? All right. So, great, I still have half an hour. All right, so let me now, we'll leave that for now. Let me get rid of the numerology. And what I want to do now is I want to start heading towards the general definition of a Coxeter group. Okay. But I'm going to do it slowly. Half an hour is good for this. I'm going to do it slowly, because what I want to do is I want to start with Cayley graphs and Coxeter polytopes. So, and basically what I want to do is I want to look at just a couple of examples. So let's start with the Coxeter group of type A2. Okay, this was one of our very, very first examples. This is the isometries of an equilateral triangle. Right? Okay, so let's go ahead and draw this example, and we'll draw it slightly big. What did we do? We said we're going to barycentrically subdivide this. Right? And then we said the 6 chambers correspond to the 6 group elements. Right? Let me remind you, maybe not all of you know the definition of a Cayley graph. If G is a group and S is a generating set, we can build a directed graph with edge labels that encodes the entire algebraic structure of the group. And the basic idea is that the vertices correspond to the group elements. And so let's say we have V sub G for every G and G. Okay? We have one vertex for every element of the group. And so here, in this example, what are we going to have? We're going to have we're going to have one vertex for every element of the group. Well, what do we have that's in correspondence with the group elements? They're the chambers. So if we wanted to build a graph, if we wanted to build the Cayley graph here, why don't we build it by putting one vertex in each chamber. Okay? So we're not just, so the idea behind a Cayley graph is a nice abstract one. For any group in any generating set, you could build this graph that describes the algebraic structure. But when it comes to the Coxeter groups, we're going to do it in a very particular way. We're going to put the vertices in the centers of the chambers. And then the edges, well, for every vertex and for every generator S, what do we want to do? This generating set is the generating set. It's a subset of the group. And what I want to do is I want to take a group element and I want to multiply by the generator and I get a new group element. Okay? That for all G and G, for all S and S, there exists an H and an edge. Well, actually, there exists an edge like this. And now I have to say what the other group element is. And there's one choice that we have to make at some point, and that is that we have to decide when we're going to take G, we're going to take S, we're going to multiply. We just need to choose whether we're going to multiply on the left or on the right. And the thing that I really want to describe is I want to describe what's called the right Cayley graph. And for the right Cayley graph, you multiply it on the right. Okay, where H is G times S. Okay? Which is G times S. So let's go ahead and do this here. Let's go ahead and do what we've done before. Let's go ahead and select a fundamental domain. And once we select the fundamental domain, then we actually know a generating set. Right? What was this nice small generating set for this example? There was a generating set with only two elements. Right? Which two elements? This reflection and this reflection. Right? And so our two generators, might as well call them A and B, are going to be reflecting across this and reflecting across that. Okay? So, and because this is our fundamental domain, we might as well declare that this is the identity group element. Right? And so, if I take the identity and I multiply by A, I want to draw a directed edge over there. Right? And so what's this? This is going to be the group element A. What happens if I multiply by A again? Then I end up back here. Right? They're reflections, and so when I do the reflections twice, I get back to where I started. And so right away, there's going to be a nice simplification that if I have G and I multiply by one of my reflections, I'm going to get over to H. When I multiply by the same reflection again, I'm going to go back. And so rather than this, let's just draw that. This is sort of a shorthand for two arrows. Okay? All right, makes it a little easier to draw. Okay. All right, so similarly, I can multiply by B and get over to there. Okay, so now I have to say one quick thing, and that is that when I'm looking at A, I'm thinking of A as a map from R2 to R2. I'm thinking of B as a map from R2 to R2. I'm thinking of these as functions, right? And so I would actually think about A applied to a point, right? And so if I wrote something like AB, B happens first, right? I'm doing function composition. And so if I start at this point and I apply the composite function AB, where would I end up? I do B first, I end up there. Then I do A second, I end up here. Right? Okay. So let's actually start labeling the point. So this is the point AB. Okay? This is the point AB. This is the point B. And let me just spoil everything. This is BA, and this is ABA, and it also happens to be BAB. Okay? All right. So now let's go over to, let's try and draw the right Cayley graph some more. So what happens when I stand at A and I look at the edge leaving, so this is it's actually V sub A, right? V sub A. So I'm at V sub A. So I'm at V sub A, and suppose I want to multiply it by B. Where should I end up? Where should I end up? AB, right? It's a little bit surprising, but I'm ending up at AB because the Cayley graph is done by right multiplication. And what that right multiplication looks like over here in terms of functions is I'm precomposing by B. I'm doing B before I'm doing the old thing. Okay? But it ends up drawing a very nice picture when we get the complete picture up here. Because what we get is we get a nice picture so that when I do A, colors are preserved. When I do B, colors are preserved. And so I get a nice graph that all locally looks the same, and as I reflect, the colors are preserved. Okay? This is a general fact about right Cayley graphs. And the idea, let me actually prove this to you. So let me actually state this as a, well, let's make it a lemma. Every group G acts on the left, in other words, as a function, it acts on the left on its right Cayley graph preserving the edge labels. And the proof basically goes like this, that how is the group acting? If I have some element, let me just call it G prime, acting on some edge between G and H with label S, this is VG and VH, well, how does the group act on this? The group is going to act, it's going to send the element V sub G over to V sub G prime G. Where's the other group vertex go? It goes to G prime H. And if you look at S, this arrow S is right multiplying. And so over here, there's an edge because G times S is equal to H. Over here, there's an arrow because G prime GS is equal to G prime H. That the group is acting on the left, the Cayley graph is multiplying on the right, and associativity means it all works. But it's important that one is acting on the left and one is acting on the right so that they don't interfere. Okay, because typically it's a non-abelian group. And so you need to separate out the two different actions. A2 tilde. All right. So A2 tilde, that's got the triangle as a defining graph. And so it should be three vectors with 120-degree angles. And so it should be some simplex with three vectors that have 120-degree angles. And so when I look at the Euclidean tiling that corresponds to, it's just going to be the nice equilateral triangle tiling. This is my fundamental domain. I'm going to put a dot in the center, and the group has one group element for every triangle. Right, continuing on. And then my basic reflections, my generating reflections, are going to be this one, and that one. Right? Okay, let me get this out of the way. And so what's the Cayley graph going to look like? So we've got, here's the identity. I haven't given these letters, but this one, let's call that A. So this is going to be the group element A. Call this one B. This is the group element B. Call this one C. This is the group element C. And then what's going to happen around here? Well, let me go ahead and start drawing it. And so what I want to claim is that if you think about this reflection, and this reflection, you start composing them, then you can actually label every vertex. Right? You can label every vertex. You can start applying this rule, and you can draw on all the edges. And all of the edges will end up being little short sticks like this. And so it'll actually look really nice and quite pretty. And because of the lemma that I just wrote, the action of these reflections will preserve colors. And so actually, what color is this edge going to be? The color of this edge. It needs to be the same color as what it looks like under that reflection. And so it needs to be yellow. Okay? Because that's the color of the edge under the reflection. How about this edge? Green, because that's the color under this reflection. And so now I think you can complete the picture. What's going to happen in the rest of this one? Green. This one is yellow, because what is this? This is the group that's stabilizing this point, and it's generated by green and yellow. Right? If you actually think about the finite group stabilizing this point, it's generated by those two reflections. You end up seeing green-yellow. And so once you recognize that, what's going to happen up here? Up here? Right? It's going to be a green-red hexagon. And then over here, red and yellow. And in particular, out of this vertex, we see all three colors. That means that the neighboring vertices see all three colors, the neighboring vertices see all three colors, all of the centers have edges of all three colors. Right? And so we know there's going to be a red edge coming out here, a red edge going there, a red edge going there, and we just keep going. Okay? And so this is the Cayley graph. And the reason why I say this encodes all the algebraic structure, if you start tracing out a path and you come back around to the same point, that means that concatenating all the labels, if you just run all the labels together and multiply them in the group, it's the identity. And so AC, AC, AC is trivial. The only thing I'd caution you about is that when you, well, let's see. So when I write down, so now I want to switch things around. So when I think about this as BA, right? If I want to think about the action that gets me from here to here, how would I do that? I would do the A reflection first, followed by the B reflection, which would be the A reflection followed by the B reflection will get me there. But if I only want to pay attention to the graph, and I just start here, that's a B edge, that's an A edge. And so I just read the labels from left to right along the path, and that also describes the way. And so here, when I think about this path, I think of it as A, B, A, or AC, 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 reading left to right, because of all the flipping back and forth with. But anyway, you end up seeing that in this picture, you end up seeing that AC cubed is trivial. Similarly, AB cubed is trivial, and similarly, BC cubed is trivial. Okay? That these are sort of obvious relations that you see from the Cayley graph. I was hoping to, and what was the diagram? The diagram here was ABC. And what are our labels? Even though we're not writing them, those are the labels, right? Because the roots, if you think about what the labels meant, a label of 3 meant that the roots had a pi minus pi over 3 angle between them, which meant that the hyperplanes had a pi over 3 angle between them, which means that when you multiply these two reflections, you rotate 2 pi over 3. And so if you take that rotation, that's a rotation, raise it to the 3rd power, it's trivial. That should all make sense with the picture and the diagram, and it's all working, right? So, if I have a diagram such as this, what are some relations that you know? AB to the 4th is trivial. AC AC, what's the label there? 2, right? Because these are pi minus pi over 2. They're orthogonal vectors, giving us orthogonal hyperplanes. And so when we multiply them, we're going to get a pi rotation, 2 pi over 2 rotation, and so those square to 1. Okay? And so, timing should just about work out, that so in the Coxeter group, let me pick one that's slightly interesting. In the Coxeter group, G2 tilde, it has relations, so actually, and here I'm hoping, most of you know group presentations? You have generators and relations? Yes? Okay, yeah, so generators, you have a set of elements, so multiplying them together gives you an arbitrary element. Relations, you need enough relations so that combining them, you can produce every relation. Okay? That's a quick and dirty explanation. So here, we know that A, B, and C are generators, right? And we know some of the relations. What do we know? We know A is a reflection. A squared is 1. We know B squared is 1. We know C squared is 1. And now we have some other relations that we know. What else do we know? Yeah, AB to the 6th power is 1. BC cubed is 1. And AC squared is 1. And at this point, you might think that you need more, right? But what I'll assert now, and we'll talk about later, is that this actually is a presentation. That those are the only relations that you need to define this group. And so now, oh, I still have 4 minutes. Okay, that's plenty of time. Okay, so in any case, if you'll trust me that this really is a presentation for the group, now you can write down presentations for all of these groups. Because the diagrams also encode all the relations. In addition to the generating set, in addition to the vector arrangement, in addition to describing the fundamental shape, these diagrams also describe all of the relations in the group. Okay? And they also describe all of the relations in the group. And so where we're going to go next is, you might say, well, what would we mean if we wrote down, let's just write down some random thing that's not on our list, where we have ABC 4, 5, 7. That's certainly not on our list. But there's a natural meaning that we can assign to this. We could say it's whatever group has the following presentation, and we can just write down what this would encode. Right? At the moment, we don't have any meaning for it, but we'll just say we could use the same technique to have this describe a group. Just the group ABC, A squared equals B squared equals C squared equals 1, AB to the 4th equals BC to the 7th equals AC to the 5th equals 1. But these are all trivial. Okay? And so at the moment, this is group G. And we don't have a lot of information about it. Right? We don't have a whole lot of information about it. In fact, just because AB to the 4th is equal to 1, it could be, we don't really know, that AB squared was equal to 1. Right? Just because I tell you that the 4th power is trivial doesn't mean that the 2nd power isn't trivial. It's not clear yet. But the hope is that because all of these had nice geometric pictures, all of these had nice Euclidean simplices associated to them, the hope is that some random diagram that we could also create some geometry. And in fact, what kind of triangle would you be trying to create here? You'd be trying to create a triangle. You'd be trying to create a triangle where one of the angles was pi over 4. One of the angles was pi over 7. And one of the angles was pi over 5. And you look at that and you say, well, I can't do that in Euclidean space. But where can you do it? For those of you that have seen this. Hyperbolic space. You can draw hyperbolic triangles with these angles. And so rather than doing Euclidean Coxeter groups, we could do a hyperbolic Coxeter group where we actually are in hyperbolic space and the triangles look more like this. And we've got pi over 4, pi over 7, pi over 5. We can reflect and they will tile hyperbolic space. Okay? And where we're going to go from here is we're going to start talking about arbitrary diagrams and the geometries that are associated to them. Okay? And they're motivated partly by the spherical and the Euclidean cases, but then these get very interesting. Okay? They're well behaved, but they have lots and lots of... They've got a nice balance of properties. On the one hand, they're well behaved. They're good theorems. You can really prove things about Coxeter groups. On the other hand, there are lots and lots of different examples of behavior. Okay? And so because you can work with them and they are strange, you can use them to build counterexamples, you can use them to test ideas, you can use them to do lots of things. Okay? It's a nice balance of things to have strong theorems and lots of strange behavior. Because then you can really try to understand things. Okay? So that's where I'll go in the second half of the course.